So what I want to do next is talk about sort of the two most basic graph primitives perhaps of them all, which is breadth and depth first search. I'm going to treat these very quickly, but most of you have seen them. If you haven't seen them or are rusty, read carefully the review reading, the first half of chapter 3. Very quickly after we blaze through these, we'll segue into DIJKSTRA'S algorithm and then talk about connectivity. Okay, so we'll see these primitives in action even by the end of the lecture today. So breadth and depth first search, which also go by BFS and DFS. So I'm just going to describe these sort of at a high enough level that it's clear that they work in either undirected or directed graphs. Okay, so they're fundamental primitives for both types of graphs, and they're going to run in linear time, properly implemented in both types of graphs. Okay, so keep that in mind. So how does BFS work? Breadth first search. So breadth first search is where you explore in kind of a cautious, tentative way. Okay? So breadth first search, both of them, you're given some starting point. Okay, so this is usually part of the input. So you start at node S, and this is called layer 0, or we're going to call it layer 0. Then the next thing you do is you explore the neighbors of S, by which I mean the vertices that are connected to S with a single edge. Explore neighbors. So this is level 1. I'll draw a picture in a second. And then you explore the neighbors of level 1, which you haven't already seen, and so forth. Now, of course, important for a linear running time would be to not keep exploring the same node redundantly over and over again. And we prevent that in just sort of the obvious way. You just keep a Boolean variable for each node, initially set to say false. We haven't explored it yet, and as soon as you explore it, you set it to true. So for example, for an undirected graph example, we could look at this graph. So if, say, S is over here, then this is going to be layer 0. Okay, so the neighbors of S are these two nodes. So this is layer 1. Okay. Now, and so then you explore on from here, and again, you don't explore anything twice, so you wouldn't go back to, S is a neighbor of this layer 1, you wouldn't go back and explore S. You would explore the not yet visited ones, so this would be layer 2. Okay? So that's the cartoon of how breadth first search works. As far as the implementation, many people first learn breadth and depth first search when you're being taught stacks and queues. These are sort of canonical algorithms which rely on the stack and queue data structures to be implemented. And breadth first search, anyone remember which one it is? Do you want a queue or a stack for breadth first search? You want a queue, right? You want to sort of first in, first out. And again, if you've never seen this, look it up either in a programming textbook or the Kleinberg-Tardosh book. Okay, totally standard first course in CS type stuff. Okay. All right, so depth first search is the aggressive search. So this is where you sort of explore as deeply as you can, as fast as you can, only backtracking when you're stuck, when you absolutely have to. So it's sort of like you're sort of trying to explore a maze. So again, you start at a given node S. And as soon as you reach a node, you immediately start exploring its neighbors. And again, as always, the neighbors which you haven't explored already. So you're always, before you explore a node, you always check the Boolean. You ask, have I already been here? If not, you just skip it. Okay? And so this is the one where you're going to use a stack, last in, first out. Okay? So keep track of next nodes via a stack, or alternatively, and probably this is how I'll write it when we talk about it in more detail in Thursday, you can just write it recursively, and then the stack is just implicit in the program itself. Okay. So probably the fastest implementations are not going to use recursion, they're going to use a stack. But conceptually, if you prefer to think of it recursively, that's fine as well. So, for example, in this graph here, again, we've started the same node S. So this would be 0. That'd be the first vertex we'd visit. Then, we'd pick one of the two neighbors to explore next. Maybe first we explore that one. Then again, we explore one of the neighbors of this guy to explore next. Maybe we pick that one, and so on. Maybe we'd even go all the way around the cycle, 3, 4. When we get to 4, at this point, we try to explore further. So what are the neighbors? Well, we could try to go here, but we've already been there, so we're not going to explore it again. We could try to go here. We've already been there. We're not going to explore it again. Similarly, we just came from here. We don't need to explore it again. So here, there's nowhere to go. So at this point, we backtrack, or the recursion unwinds if you prefer. And at this point, we've visited all of the nodes, okay? And the stack will pop completely off, okay? So here we visited the nodes in this sort of clockwise order around the cycle, as opposed to this layer-by-layer visitation scheme that breadth first search gave us, okay? So those are cartoons of how the two algorithms work. So I do expect you, to be able to write down, pseudocode formally if you haven't seen it before. So you should look up the details if you haven't seen it. I also definitely expect you to know that both of these algorithms run in linear time. Okay? And again, just to be general, I'm going to write O of n plus m. Okay? Number of nodes plus number of edges. You guys go ahead and look in the book or in your 103 notes or what have you. But just what's the idea of why they run in linear time? Well, so first of all, they're only going to visit any given node once. And we just sort of force that because we have a Boolean and we just check, right? So before going to a node, we make sure we haven't been there before. And then the claim, and you should think this through, but I hope it's reasonably believable, is that each edge you're going to look at most twice, once from each of its endpoints. Okay, so an edge you look at it once when you first explore across that edge, and then at one point when you reach the other endpoint from the other side, and you're not going to, that'll be the final time. Okay, because you never visit an edge more than once, a node more than once, you're never going to look at an edge more than twice, once from either endpoint. Okay? Because when you visit a node, you look at each of the edges around it only once. So that's the basic reason why it works in linear time. All right? Okay, so that's the breadth and depth first search review. As I said, we're going to be using this over and over again. We'll use it in lecture multiple times. I can assure you you're going to be using it on homework. I can assure you it's a better than 50-50 chance I'm going to be either explicitly or implicitly asking you to use it on the final exam. Okay, and I think you'll find uses for this after the class. Maybe the most fundamental graph primitive. So any questions about it? Or about them, I should say?
It's so important. Is there a more optimized way of doing these graph searches that are less than linear?
So it sort of depends what you want to accomplish. You could imagine versions where you don't care about looking at the whole graph and you only want to look at a local region. In that case, the answer is yes. If you're trying to do anything which in principle depends on the entire graph, then you do have to look at the entire graph. So that would require linear time. But it's a good question. Sometimes you do want to optimize this where you effectively stop early. So you say, look, I know this is the important region of the graph. I'll give you some point in the middle of this important region, and then you'd stop the search after some period of time. So especially like with breadth first search, it's very easy to imagine how you do that, where instead of waiting till it finds the whole graph, you just stop it after 10 layers and just work with that sub piece of the graph. So they are quite amenable to, tweaks for domain-specific goals. Other questions?